Hey folks, welcome to the Geek Narrator. A few days ago, OpenAI published a fascinating blog post about how they have scaled Postgres SQL to serve 800 million users. And if you are like me, you probably thought, wait, OpenAI, the company building GPT, they are dealing with the same Postgres challenges we all face? And the answer is yes. And what's remarkable about this blog isn't that they are doing anything revolutionary, it's that they are doing the fundamentals really well. Read replicas, connection pooling, query optimization, all the things we learn in system design but rarely see applied at this scale. Here is what makes this interesting from a technical perspective. They have a single primary Postgres SQL instance serving writes for their entire platform. That's ChatGPT, the API, all their products, one write node. And yet it works. In this video, we are going to break down why a single Postgres primary becomes a bottleneck at scale, how MVCC creates unique challenges for write-heavy workloads, the specific optimizations OpenAI applied at each layer, at every layer, from read replicas to query patterns, and critically, what you can learn from this for your own systems. Let's get into it. Hey folks, let's start by looking at the simplest possible architecture of your application, how it looks like when you are just starting up, right? When your architecture is simple, your requirements are simple, you don't have that many users, and it makes a lot of sense. So what you have here is your users making requests, and then you have a load balancer to distribute your requests to your application. You have a bunch of application nodes, and then you have a simple primary database that serves your reads and writes. And then you may have one or two read replicas that you may choose to offload the reads and so on. And you may have some caching mechanism like Redis or Memcache. So this is simple. This is a beautiful architecture. It works when you're starting up. There are no problems at all, because you don't know that your system or your application or your product is going to have 1 million users or only a few hundred, right? So for that, I think it makes a lot of sense. But what happens when your users grow, when your product becomes successful and you have a ton of requests, ton of more requests coming up, and they are going to your database and then hammering your database? It creates some problems. So what are those problems? Let's look at that. So let's say, like in case of ChatGPT or OpenAI, they had 800 million users, and of course with every feature release you might have seen that they get a lot of surge in the traffic, a lot of incoming requests, people want to try out the new features, and it gets tricky because you only have a single primary database node which is serving your read writes. You may have some replicas, that is fine, but at the end, this is your bottleneck. This is a single point of contention and single point of failure that you have. So you have increased traffic. You can, of course, to scale the reads and writes to perform better, you can scale up the machine, right? You can vertically scale this machine by providing more resources. AWS, Azure, GCP, they'll be more than happy to provide you 24 terabytes of memory and all the resources you want. But it's expensive, and more importantly, it has a limit. You can't do that you can't do that forever, right? So that is the reason you need to look at other parts of your system. Hey, where can I make things better in my application, in the way I'm querying, in my caching mechanism? Should I have more read replicas and so on? And there are a bunch of mechanisms that you can do, you can take a look at. Before we go further, OpenAI also highlighted that they faced some specific challenges related to the MVCC concurrency control, which is what Postgres uses to provide you concurrent mechanisms. So multiple transactions can come and access your data. And the beautiful part about MVCC is that your readers do not block writers, and your writers do not block readers. And this improves the performance by a lot, because a lot of transaction, if your application is read heavy, you won't be blocking any writes that are happening, right? If your application is write heavy though, there might be some problems and it might get amplified because of MVCC. And what are the problems? It lies in the fact how MVCC works, right? So whenever you want to update a row or write something, instead of updating that row in place, what Postgres does is it creates a new version, right? What it does is, instead of using locks to basically provide some sort of synchronization between different transactions, it creates a copy, right? It creates a copy such that, let's say you have your transaction 1 and transaction 2 coming up, right? So what transaction 1 will have is a separate snapshot of the database as compared to transaction 2. And then they can both operate on their own snapshot depending on what they want to do. They might end up having a conflict or not, but they can perform independently in isolation in different snapshot. And if you're not aware of how different transaction isolation levels work and what are the anomalies, I highly recommend you watch this video that I created. It will help you understand the different anomalies that may occur. But in short, Postgres uses MVCC. It creates multiple versions. So each transaction gets their own version. They can work with their own snapshot. But the problem is there is heavy amplification when it comes to writes. And if your application is write heavy, you may have a lot of data that is written for a single row. So what OpenAI observed was, for their write heavy workload, index bloat is a major problem, that your indexes are also bloated. For a single row, they have a massive index because of the multiple versions. To maintain auto vacuum and to tune it properly is a complicated thing, because you have to keep a balance. So auto vacuum is like this garbage collection style mechanism which will take care of your dead tuples and your rows that are deleted and so on. So it keeps the balance between the number of versions you have versus the IO it has to use to perform this, similar to garbage collection. So it is complex because you need to tune the auto vacuum process that is running. If you use a relaxed approach, you may have index bloat. If you used an aggressive approach, you may have higher IO usage that may impact your database performance. In short, in some write heavy workloads, depending on the query patterns, MVCC creates more challenges, as OpenAI also mentioned. So in short, the strategy revolves around the single point of contention and single point of failure. Okay. Now let's think about this. If this primary database or the primary node is a single point where the contention is happening and where the scaling has a problem, the main strategy is to reduce the load on the primary database. And how can we do that? We can offload the read-only workload to specific read replicas. In this case, they had 50 read replicas, right? So these are like copies of data serving in multiple regions and multiple nodes of databases, and then they only serve read transactions, right? So what happens is, if your application or certain features are read heavy, they won't touch your primary. They will directly go to read replica and serve the request. This means we are offloading the reads from the primary to the read replica. Now again, 50 is a lot of read replicas and it might not be the best practice. It has different problems that we'll talk about, because it requires replication, because where is this copy maintained from, right? It is coming from the primary, and it might have some problems when it comes to the replication. We'll talk about how that is also mitigated using some strategies. But for now, let's keep in mind that reads can be offloaded to read replicas. You can have many read replicas. It has a limit. In this case, they had 50, which works fine. But we cannot move all the reads to the read replicas, because there are some reads that are coupled with writes and they are within a transaction. So not all reads can go to here, but reads that are coupled with writes, within a transaction, they should still go to the primary node. Otherwise, there might be some consistency problems that you will face. So this is a great way. You can scale up or scale out the number of read replicas you have. You can deploy them in multiple regions. So it's all good, and you can easily move your reads to this cluster. It is great. So what we have achieved so far, taking away some load off the primary to read replicas. Okay. One other thing that they have done is, since we talked about that not all transactions are read only, there are some reads and writes. What they have done is to reduce load further from the primary database. What they have done is they are using a cloud offering called Cosmos DB, which is a highly available, globally distributed, NoSQL and SQL support. It has multiple data model support. It also supports vectors, low latency. Since it's a managed service, they don't have any operational problems here and operational efforts that are required. So what they are doing is all the features, all the user requests that are shardable, that can go to this distributed database, they are trying to move away from the regular primary Postgres deployment, and then they go to the Cosmos DB. So all the new workloads typically go to Cosmos DB. There are some features and user requests that are not shardable, that has to go within the primary database. They still go here. But the point is reducing load on primary, and they're actively moving away workload to Cosmos DB. Keep in mind that this Postgres database was not sharded by them, but they don't rule out this possibility that they might need to shard this database further. So you may have multiple primary sharded deployment, so they can serve different use cases, but they haven't done it so far. So there is still one single primary, but they are moving away the load to Cosmos DB wherever possible. So again, this is about using the technology which is best suited for a given use case. If for shardable user request, they can definitely go to Cosmos DB, and for use cases where the simple primary Postgres shines, they are still using it. Moving on, what are some other things we could do to reduce further load from the primary? It's very important that you observe your queries, what is happening, right? Coming from the application, you are exposing some user features, and users are making some different API calls, they have different data, and they might end up, translating that simple user request into some complex, expensive, slow joins on your database. So what they did was they observed that some of the joins were involving multiple tables, like a lot of tables, having complex joins, which were slow and expensive. So this was another problem, because when your queries are slow because of joins, it also consumes a lot of CPU resources. It takes time to execute. Connections are occupied for a longer time. Sometimes due to this slow response, your queries will also time out. So there will be a timeout, and then because of configured retries, there will be more requests and more load on the database. So it is important for you to understand what kind of queries you are running, and then optimize joins and queries as required. In this particular case, when they had so expensive joins, what they have done is also pretty interesting, and also, not always suitable, but in some cases you can easily do it. So what they have done is, instead of letting the database join so many tables and ending up consuming a lot of resources on your single primary database, what they have done is they have offloaded this to the application. So now application makes multiple queries for the data that it needs. So it requires few tables for each single query, and then it gives the response back to the application, and then the application is responsible for joining the data and doing whatever it needs. So what is happening here is that this computation and the resource requirements are moved from the database to the application level. The queries are faster. It is not taking a lot of resources on your primary. Again, not always suitable. Does it mean that joins are bad? No, not at all. Joins are really powerful. But in some cases, when joins are expensive, don't shy away from thinking out of the box, moving those things to the application if it makes sense for your use case. But there's no one way of doing things, right? Both have their own challenges. In this case, if you want to join on the application level, First, you have to write more code, you have to maintain that code, you have to test it properly. If this logic is also replicated elsewhere, let's say you also have a mobile client, you have to replicate the logic here, and then there's a lot of maintenance load. So it works for them, it may work for your use case, so think about what you can do. Another common problems we all have seen, I'm pretty sure, and common complaint that developers have with ORMs, which I don't necessarily agree with, is that sometimes usage of ORMs blindly without understanding the queries that are generated by the ORM framework, it can have problems, right? But then it's not the ORM problem. So we shouldn't blame the ORM, but we should try to understand what the queries are that are generated by our simple abstraction that the ORM provides. And then if it's really expensive on the database, if there is a chance for you to optimize on it. So observe the queries, and if your ORM abstraction is creating query amplification, there is a high possibility that you are using it incorrectly, or there is a better way of implementing it. So take a look at that and try to optimize your ORM queries. For example, you make one request and you just make a simple API call on your ORM that translates to loading a lot of data or making a lot of requests from your primary database, and it creates some problems on your primary database. It's not that difficult to log your queries generated by ORM, explain them, understand what's going on, follow the best practices of your specific ORM framework, and then make it work. So the thing is, try to go beyond the abstraction, understand the problems your query patterns are going to create, and then try to solve it. Otherwise, of course, you will face some problems. So as you are seeing that optimizing or scaling your database is not only about just providing more resources to your database, it is also about thinking from a perspective of systems thinking, where you are looking at each of these components, each of these areas where you can optimize and do something to take away the load from your primary. Keep thinking about the entire application and not just one part of it. One big thing that is still a problem is that even if we have taken away the reads, we are moving the active workloads to some other database, Cosmos in this case, we can't ignore the fact that this primary is a single point of failure, right? If this database goes down, it's going to crash and your application will be down. So what they have done is they have maintained a hot standby, right? And Postgres supports both synchronous and asynchronous replication. By default, if you enable streaming replication on your primary, it is going to be async, which means as soon as the transactions are written, they are written to a write-ahead log. If you're not aware of what is write-ahead log, if you do not understand how it works, please take a look at this video. I've explained that in detail in terms of databases. Whenever the entry makes it to val, it is then replicated to the replicas, in this case hot standby, and it can be done both in sync and async manner. So when you are doing synchronously, what is happening is whenever there's a call made from the client, it is also written to one of the standbys, and if this call is successful, only then the response is sent, right? Which means that this is better in case you care a lot about the durability of your data, which means if a transaction is committed, you are sure that it is written in two places safely. For asynchronous, what happens is your API request, your transaction will be committed, it will go to a wall, and then asynchronously it will either streamed, as in when the transaction is written to wall, it is replicated to hot standby, or in a file-based approach, it is done in small batches, which has a higher chance of data loss if your primary goes down and the replication was not done, if you are using batched approach. And if you are using streaming approach, the changes go as soon as possible. So what they have done is, what I think, it's not very clear from the blog, but what they have done is they are using streaming replication to keep a hot standby up to date. So whenever your primary goes down, your application can start using the hot standby, and this becomes the new primary, right? So the point is that you need to maintain a hot standby or a replica that is serving reads maintained asynchronously or synchronously. Of course, if you enable synchronous, you get more data durability guarantees. But of course, there is some latency involved because you are waiting on the transaction to be written to two machines instead of one machine. But if you're using async, it is still high durability guarantee because in most cases, depending on how many resources you have on the hot standby, it will be very quick to apply the changes that is streamed from this hot standby. But then it also consumes resources on the primary to keep streaming these changes to the replicas you have and so on. So it's not straightforward, but it works. It's a proven pattern. So take a look how to enable sync, async, particularly to Postgres. It's very interesting, and make a decision based on what is more important for you, okay, and what are the failure modes you may have in your application. So far we have seen that we are trying to remove or offload the primary from a lot of requests. Like we used read replicas to scale out the reads. Read-only transaction go to read replicas. They don't touch the primary. Then you have hot standby. So in case the primary goes down, your hot standby can take over and your application won't have a lot of downtime. You also have new workloads, shardable workloads move to Cosmos DB. You also have caching and different mechanisms, but there is more you can do, right? What you can also do is you can prioritize the workload. Again, understanding your application, what kind of features and user requests are coming in. You can prioritize your workloads and pass user requests to certain different database nodes. As in, for example, this is priority 1. So all your, let's say, paying customers go here. When you have certain features that are more critical than random features, you can go to the high priority node. For all other, you can distribute the workload based on the priority. So in this way you have certain isolation. So let's say this feature or this type of workload gets a surge in traffic. So all these requests will keep coming in this database node, but it won't affect these two other nodes, or let's say priority based workloads. So this is another possibility you could do. So you could still, it's like having a different database for specific use cases and not bombarding a single database. So it's highly specific to a certain use case. You may not be able to do it. You may be able to do it easily, or you may be able to do it based on some refactoring on your application. But it's a good strategy to isolate. One thing we talked about earlier is that, so there is a primary, there is a bunch of read replicas, in this case 50, and it's quite a lot. It's not typical. Typically there are 2-3 read replicas, but at high scale, OpenAI is using 50 read replicas. But the problem is this replication is done from the primary, right? And if you have enabled streaming replication, standby nodes will have, let's say, a replication slot or a TCP connection open. The primary needs to stream these val logs to each of these 50 read replicas. And it's a lot of compute. It's a lot of work that the primary has to do. A lot of connections that needs to be opened. So it can also be a problem. So it's not very straightforward. So the mitigation for that, or to avoid any problems on the primary because of replication, there is a strategy called cascading replication. And again, I'll link a document about how it is done in Postgres specifically. So take a look. But the idea is that instead of letting the primary do all the work for all the 50 read replicas, what you do is you use intermediate replicas that is like relays your val logs, and then primary is free, right? Primary is free. It doesn't have to replicate it to 50 nodes, but then these intermediate nodes will replicate it further to the other read replicas. So in a way, primary is doing it only to the relay nodes or to the intermediate replicas, and then intermediate replicas are the ones who are doing the heavy lifting of replicating across the different 50 replicas you may have. So it is another important strategy to offload the primary from doing a lot of work that is not important, that is not serving your user request. And it's an important one. So take a look how it works. It's really interesting. Great. So we have seen a lot of other strategies to reduce load from your primary database. But then even for your read replicas, if you're not efficiently using the connections available in these read replicas, you may still go out of the connections. you may still need more number of machines and so on. Efficient connection pooling is important. So what OpenAI has done, they have used a PG bouncer proxy, which efficiently manages the connection pooling in the right mode, and there are multiple modes available depending on your use case. You could use these connections wisely and reuse them whenever the transaction is over. So an efficient connection pooling is critical. So I think they have 5,000 connections on each of these nodes, and reusing them enables more number of requests to be served with fewer read replicas. Otherwise, if you're not reusing them, or if you're not using them efficiently, you may need to scale out to more nodes, which is inefficient, costly, and creating more problems on the primary node. So this is another thing that they have done, and it's very important to understand. With this, we have seen multiple strategies, how it all works to take away this load from the single point of contention, the single point of failure that you have. And there are so many different strategies when it comes to this architecture. And it's a very common architecture. There is nothing unusual about it. But tremendous engineering has gone behind this. And it's not a usual thing to have 50 read replicas. But I'm pretty sure that they have done a lot of experimentations, a lot of observability improvements to understand the query patterns, to understand the queries they are running, and so on. So these were the strategies that OpenAI used. So what can we take away from OpenAI's approach? First, there is no magic. They are using read replicas, connection pooling, hot standby, all patterns that have existed for decades. The execution is what matters. Second, know your bottlenecks. Their entire strategy revolves around one constraint, the single primary Postgres instance. Every optimization flows from that understanding. If they had tried to optimize randomly, they would have wasted a lot of effort. Third, database optimization happens at every layer. They optimized queries, reviewed ORM patterns, tuned replication, configured connection pooling. Scaling is not a single layer problem. Fourth, choose the right tool for the job. Moving shardable workloads to Cosmos DB isn't abandoning Postgres. It's using each system where it excels. And finally, this architecture isn't typical. 50 read replicas is not normal. A single primary serving 800 million users is not recommended. They acknowledge this. There are historical reasons, and they are working on long-term solutions like potential sharding. The goal isn't to copy their architecture. It's to understand the principles, reduce load on constrained resources, scale horizontally wherever possible, and optimize relentlessly at every layer. Remember, every layer. I hope this breakdown was useful. If you want me to cover similar deep dives on other engineering blogs or other topics, let me know in the comments. I'll link the original OpenAI blog post in the description. If you found this valuable, please hit the like button and subscribe to the channel. I will see you in the next one. Thank you.